ferrites. It is a power ferrite designed for high flux densities, and the material was a Ferrox Cube 3C30 material. I won't show the manufacturer's data sheets, but I can show another reference book which I use, which is this one by Snelling. It's an older book, but it is very good for the electrical engineering properties of ferrites, and it had another ferrite material very close to the one that I used. So I had two independent references. Actually, there are a few more graphs in the Snelling book than there were on the Ferrox Cube company's data sheet. So I was able to get the properties that I needed out using those two references. And I'll show you very simply how I did it here. Here was my initial attempt to translate the manufacturer's data into a function that I could use programmatically. And I used a polynomial power series expansion initially, but it didn't work. And you can see the yellow curve there is as close as I could get to the manufacturer's curve. And incidentally, some manufacturers are starting to put these curves out as functions. I couldn't find any for ferrites, but I know in the power semiconductor industry, they're starting to put the curves out as functions rather than graphically, so that we can use them in our programs. So my first attempt at using a power series had ripple on it, even when I went up to 15 terms in my power series, and the negative ripple there, the negative slope of the ripple, precluded the QuickField from solving it, from converging to a solution. So I had to turn to another reference, which I'll show now, which is a famous classical work by Bozorth. I think it's essential reading for anybody involved in magnetic materials. And he suggested the use of a hyperbolic tangent function, which I ended up using, and that gave a very smooth curve. So I can show the resulting family of curves here. These are generated by the hyperbolic tangent functions. When I write a program to solve problems in QuickField, I also make the same program generate an archive, a file of the properties that were actually used to run the model, so that if there's ever a problem, we can come back to that and check that the properties were correct. I do visually check them, but it's very good to store an archive of the properties that were actually read into QuickField or loaded into QuickField, along with the results of the QuickField files. So I can illustrate the BH curve in a 3D format now. We can see that on the front base axis here, this is a 3D graph, we have temperature up to 200 Celsius, a little bit hard to see there. And when the ferrite material is cold, the magnetic properties are better, meaning that we get a higher flux density for a given magnetization field. And it roughly follows the Curie-Weiss law, so that as the temperature of the material approaches its Curie temperature, the magnetic properties diminish. And I was able to obtain functions out of the two references I mentioned, the manufacturer's data sheet and also the Snelling book. I was able to obtain functions here which fairly closely replicate the graphs shown. So I have a function. I made it a product function. I had the BH curve using the hyperbolic tangent in this direction, and then I multiplied that by the replica of the Curie-Weiss curve, which is not quite true for a complex material like a ferrite, where they actually tailor the crystalline structure to modify the Curie-Weiss curve. But that was the best I could do in the time I had, and it's fairly close to the real properties as far as I could see. The other nonlinear property I had to do, and I go back to this one. There are two ways to find the core loss in the ferrite device, which I needed for I had to couple the core loss into the thermal solver to see how hot the ferrite gets. There would be two ways to do that, and both ways would be valid, and I chose probably the simpler way, but maybe not the best way. One way would be to use a QuickField, two successive coupled QuickField solvers, one with the blue part of the BH curve or the hysteresis curve and one with the red part. I think it would be possible to do that, although I didn't try it. The method I chose was to use what's called the Steinmetz function for core loss in a magnetic material, which, according to my reference spelling, accurately, he did some tests and he showed that the Steinmetz function fairly accurately replicates the core loss. So I used the curve there called original trajectory. I gave that to QuickField. And for core loss, I calculated it using the Steinmetz function, which I'll show a little bit later, which bases the core loss on the peak flux density in the sine wave and also the frequency. It's a power series. It's actually the peak flux density to the power 1.9.